Hi. In this new episode, we'll continue on the Bayesian persuasion problem and try to discuss the optimal persuasion or the optimal signal, and try to understand that when the senders can really benefit from the persuasion. Okay, so let's do this. So we'll discuss about the optimal persuasion or the optimal signal. Okay, so we'll talk about the same thing here. And of course, we continue on the paper from Kamenica and Gentzkow, 2011. Okay, so we know that the sender can actually benefit from persuasion if and only if there exists a Bayesian, a base plausible tau such that the expected utility for this sender over the tau, given some posterior belief of the receiver. So this expectation of the expected utility for the sender must be higher than the payoff for the sender given the mu naught, given the prior, right? So that's the critical. That's the condition that we are going to state here to discuss when the sender can actually benefit from the persuasion, right? So that's the key idea here. Okay, so sender benefits from a persuasion. Okay. If and only if there exists a base plausible tau. So tau, as we mentioned in the previous episode, so tau is just right. Remember that tau is just the distribution over the posterior beliefs, right? So which is an element of delta omega, right? Okay, so there exists a base plausible tau such that, as we just said, so the expected utility of the sender, given some posterior belief of the receiver's belief, then its expectation is over the tau using tau's density or the probability mass, so which is greater than the sender's payoff, given the belief is just the prior belief. Okay, so that's pretty simple. Okay, so and also, so it's very natural to further think that so the value of an optimal signal is just the maximization over tau. So it's maximized over the expected value of the sender's payoff, right? Over tau. V hat mu. Subject to. So the condition which must be satisfied is the base plausible, right? So the expectation of the posterior is prior, okay, and summation over the support of the tau. Okay, so that's basically the idea of this. Some conditions for the when the sender can actually benefit from persuasion, right? So some useful note to say here is that because this game is concentrating on the sender preferred sub-game perfect equilibrium, right? So we're using the sender preferred SPE, okay? So actually this thing guarantees us that the fact that V hat is upper semi-continuous So if v hat is upper semi-continuous, then this thing ensures us that the existence of the optimal signal. Okay, optimal signal. So it's actually it's the upper semi-continuity of the v hat gives us this existence of the optimal signal. Okay, and which is under this a solution concept for the Sanders preferred subgame perfect equilibrium. So, and that is not directly derived from this this result here, right? Okay. All right. So to visualize this, okay, we need to define some function. Okay. So as what defined in their paper, so v, this is a capital letter v of mu, which is a superior set of z. So for this that, we have something similar, pretty familiar to us from the previous episode, which is the mu and this z point. Okay, so this point is in the set of the convex hull of v hat. Okay, and we put all those z together, and so basically the z is the remember that we have sort of the this is the value of the v hat mu, right? So this is actually the just the value of that signal. So, and we put a superior here to just denote that this is actually this capital letter V is concave by the construction here. Okay, and this V is actually, this function is the smallest concave function, and which is everywhere greater or equal to the small v hat. Okay, so this V is concave. This is by construction, and it's the smallest concave function everywhere no smaller than v hat. Okay. All right. So intuitively from the picture, we can have something very pretty interesting. And let's just take a look at this little picture here. So if we have mu on the horizontal axis, okay, and v hat on the vertical axis, okay, and we'll also have some other functions, but we'll have v hat for sure first. Okay, so let's say that this v hat of mu looks like something like this. Okay, so that there's a very obvious convex hull. So okay, right. So this function is v hat mu. Okay, all right. And obviously this hull here is the convex hull. Okay, literally. Okay, so the capital letter V is something like this. Okay, so let's do it on the red color, a thick line. So it's the smallest concave function, which is actually, it's enclosing this v hat mu function. Okay, but it has to be a concave function, so it fills the gap of the a little v hat function. Okay, so it should look like this. Okay, so from here it should fill this gap, and then it goes the same as v. Okay, so this is the capital letter V of mu. Okay, so that's it. That's the meaning of the big V function. Okay, so the reason that we can use a two-dimensional picture here, and we only need to actually have only one mu here. Okay, so this is the reason is that we have we only have two elements, or we have a binary state space. Okay, so in this case, then we can actually we can only use one real number to denote one of those two probabilities, right? So it means that specifying one probability, then this actually it can uniquely pins down the entire distribution of mu, right? Pins down the entire distribution of mu. Okay, so that's the reason that we can only use one real number here to denote this whole distribution here, because we only have two elements. That we can use one minus this to get the other one, right? Okay, so good. So that's the meaning of that. And we already know that, right? So from the previous proposition one, and we know that, for example, if let's say if mu naught is somewhere here, okay, say it's just here. Okay, so let's say that this point here corresponds to mu L, and this corresponds to mu H. Okay, and so later we'll see that actually, so we already know that, right? So this actually, by persuading the receiver, okay, so the sender can actually commit to some signal, and then this signal can actually induce a distribution over the positive belief. So it means that this, by giving this signal, okay, by committing to this signal and then reporting the signal realization, so this mu naught is actually redistributed, or right, so from mu naught to mu L and mu H, okay, with some probabilities, okay, and those probabilities, okay, so this and that, so those probabilities together, they form this tau, right? So that's the meaning of tau. So tau specifies those two probabilities that for by which the mu naught is redistributed to mu L and mu H. So that's the meaning of tau, and that's pretty simple, right? So by doing that, what we can get from this picture for the sender's utility is that actually, if the prior is mu naught, then the sender would originally get this utility, right? But actually, because the mu naught now is redistributed to two different posterior beliefs, then actually they have those 2 points as the sender's new expected utility. And then if they take the probabilities, then they take the expectations, then actually it's this point. So this point should be just right above this point, right? Because they have those two probabilities here, and this is a linear here, right? Okay, so actually what we are doing here is that by giving this tau, right? So by giving a pi, right? So this pi is actually redistributing this mu naught to mu L and mu H. Then this v hat given mu naught is actually it's increased from here to here, right? So that's the by redistributing them to those two different posterior beliefs, then this is expected utility of the sender increased. Okay, so that's the core idea of the Bayesian persuasion, right? And this is just shown in this picture. Okay, and of course we will have something more rigorous to describe this fact. Okay, so before that, we noticed that this capital letter V, so big V mu, this is the largest possible payoff of actually that the center can achieve, right? Achieve with any signal if the prior is mu not, right? Okay. All right. So what is the value of the optimal signal here? So it's obviously is big V mu naught, right? So we have the other corollary, okay? So we don't need to number those results. We just state those things here, okay? Because we were not going to prove those. So the value of an optimal signal is just big V mu naught, right? It's just here, big V mu naught. Okay. And of course, standard benefits from persuasion if and only if this big V mu naught is higher than the small v hat mu naught, right? Than the original priors related v hat, right? So that's the basic idea of this this thing here. All right. Good. Okay, so now we are quite familiar with those formal statements. Then we can start to take a look at an example, specific example. Okay, so we adapt the same example from their paper, which is the story between the prosecutor and the judge. Okay. All right, let's do that. So this example will help us to better understand this model, the Bayesian persuasion model. Okay, so example. So we have this prosecutor. Okay. So the prosecutor is the senator, right? And the judge is the receiver. Okay. So this prosecutor is trying to convince the judge that a person or this defendant is guilty. Okay. So the prosecutor, so this is just the assumption of this game. Okay. So it's the reality might be different. So this is just the game by assumption. So the setting. So this prosecutor would always try to persuade or try to convince the judge that this person is guilty. This is because the reason is that just by the setting of this game. Okay, so this reason is that this prosecutor wishes that the if this person or this defendant is guilty by the result from the judge, then this case is sort of the good case for this prosecutor. Okay, so then if no, then this case is wasted, right? So that's basically the thing that they assumed in this example. Okay, that might not be realistic, but that's just an example. Okay, so if this person is guilty, okay, all right, then actually the full review or the full revealing is helpful. Okay, so it means that this judge can now say that this person is guilty, and then the prosecutor is also happy. Okay, but if this guy is innocent, okay, then the full revealing, it will hurt the case of the prosecutor, right? Because this is sort of it affects the successful rate for prosecuting some person from their perspective. Okay, let's say in this way. So then this is then revealing is hurting their case. Okay. So this means that those statements simply give us some underlying assumptions for their utility functions, right? So then we can actually model from this background. So the question is that how to really structure the arguments from the prosecutor so that they can increase some probability of the conviction by a rational judge on average. Okay, so here there should be another implicit assumption that this judge is they're rational. It means that this judge is sort of acting in a Bayesian way, right? And because we're doing something on average and trying to improve the welfare the utilities on average. Okay. So, all right. So this object for the prosecutor is to how to structure a better statement, okay, to increase the probability of conviction. Okay. And of course this is done by a rational judge. And it's on average. Okay. All right. So the basic setup is that specifically, the judge must choose either acquit or convict, okay, this person. And the state, of course, we have state, is either this person is innocent or this guy is guilty, okay? So those are states. So as we just mentioned, there's some assumptions for the utility functions. So specifically, the utility is that the judge utility is 1, okay, if those are matched. So it means that if the person is innocent and this judge acquits this person, then this is matched, so it's 1. Or if this person is guilty and the judge convicts this person, then it's also matched. So and then this is also 1. Okay, so both work. Otherwise, it's 0. So if not matched, okay. So if this judge sends a good guy to prison, or this judge just let a bad guy go, right, wrong way. So that those are not matched, and this judge gets 0 utility. So on the other hand, so prosecutor, okay, gets 1 if convicted. Okay, so the prosecutor actually doesn't care if this is a good guy or not. So as long as this guy is convicted, then this prosecutor is happy. Okay, otherwise it's 0 if just acquit. Okay, and of course we have some prior. So we specify that the mu naught given guilty is 0.3. Okay. So because we are talking about the Bayesian persuasion, so we'll have some signals. So intuitively, in this example, the signals could be some so-called investigations or some evidence. Okay. All right. And so those refer to the signals. So the pi given guilty or the pi given innocent. Okay. Those probabilities. So the prosecutor commits to a pi, and this prosecutor must truthfully report this signal realization of this committed pi, right? Okay, so that's the standard setup of this game, the persuasion game. So let's analyze this. So first, if the prosecutor is always fully revealing the state, so what if that happens? So first, a full revelation. Okay, so this means that pi of g given g is 1, right? G means that this guy is a bad guy. Okay. Is guilty. Okay, and pi of I given I is 1. Okay, so those are pretty simple signals. And then this means that the judge will convict 30% of all time, right? So convict 30% of the time. And this is because that the prior is just 30% or is just 0.3, right? Because of the full revelation, and the judge is okay. So let's now we can write something more specific. Okay, so the prosecutor payoff is 1 times 0.3 plus 0 times 7, which is 0.3. Okay, and this is actually we need to multiply 1. Okay, so we don't need to do that. But so this means that this 0.3 means that because the judge is acquitting 0.3 out of 1 of all time, right? Based on that, the prior is 0.3, which is the ratio of the guilty guy, right? So this is actually the right. So in this case, the prosecutor gets 1, right? If because this is fully revelation, and 0.7 of the time, then the judge will let the person go, right? So it's acquit. So it means that this probability is this payoff for the sender for the prosecutor is 0. Okay. All right. Yeah, that's it. So we don't need to multiply anything else on top of it. Okay. So that's the full revelation. So how about no information? Okay. So what if this prosecutor is babbling all the time? Okay. So let's say that pi babbling. So babbling means that saying something all the time. So saying something all the time, the same thing all the time, means that saying nothing all the time, right? So there's no useful information. Given g equals to pi babbling given I, okay, equals to 1. Okay, so in this case, then the judge will always acquit, right? Always acquit. This is simply because that the mu naught is 0.3. If mu naught is higher than 0.5, then the result is always convict. Okay, so that's the simple reason for that. So in this case, prosecutors payoff is 1 times 0 plus 0 times 1, and it's 0. Okay, So this is a pretty interesting result. So the first part here, the first one is the probability. Sorry, this is the utility, okay, of the prosecutor if convict, okay, and this is the probability of convict, because it's not possible to convict all the time, and this is the probability of acquit. So they're acquitting all the time, and this is what they get, what this at center get, what the prosecutor get, right? So this is the utility of acquit. Okay, then finally this is 0. Okay, so the center gets nothing here. Okay. All right, so this is the no information. How about something in the middle? Okay, and the center provides some signal. Actually, here, just for simplicity, we just give the optimal signal here. We don't need to bother to give another second best signal. We just give the optimal signal. Okay, so some signal which is in the middle of the full revelation and no information. And actually here, this is the optimal signal, which is simply saying that the center can do better than the no information or than the full revelation, right? So here the set of the signal realization is small g and small I, okay? So guilty or innocent, some signals and realizations. So pi of small g given big G is 1, okay? And later we'll verify this. Okay, and pi small I given G is 0. So this means that if this guy is guilty, then the probability of this prosecutor is sending that this guy is guilty is 1. So of course, the prosecutor is saying that this guy is innocent is 0. The probability is 0. On the other hand, given I small g, the probability is 3/7. And given I, the probability of small I is 4/7. Okay, and this is somehow pretty interesting right here. And this is the part of the optimal signal, right? And later we'll use a little picture to show why this is an optimal signal and the interesting part of it. Okay. And here actually this the sender and actually sender and both sender and receiver, they are better off than before, right? Okay, and later we'll of course we'll show the results and we'll verify the result of this signal. Okay, now let's do that. So in this case, okay, the judge's payoff from convicting if a small g is received. Okay, so this payoff goes to pi of small g given big G mu naught big G, okay, and over pi of small g given big G mu naught G, and plus the probability that the person is innocent, but the small g is sent, right? Given big I plus mu naught big I, okay. Okay, so this is simply nothing but 1 times 0.3, right? Over 1 times 0.3 plus, this should be 3/7 times 0.7, right? Okay. Okay, don't mix up with those priors. Be careful of the notations. So this is simply 1/2, right? A half. So again, judges pay off, but from acquitting if a small g is received. Okay, so it means that the numerator is that this person is innocent, right? But who's receiving a small g. Okay, and the denominator is which is the same as the above, right? Mu naught g plus pi I mu naught I. Okay, and this is 3/7 times 0.7. 1 times 0.3 plus 3/7 times 0.7, which is 1/2. Okay, let's see if we did this correctly. Okay, this is 3/7. Okay, I is 0.7. Okay, this is the same. All right, no problem. So so those are the same, okay, in this example. And then in this case, we select the Sanders preferred subgame perfect equilibrium. Okay, so that's the how this is defined, how this solution concept is defined in the paper. Okay, so let's calculate the payoff for the prosecutor. Okay, so the payoff for the prosecutor is pi little g given big G mu naught g, okay, plus pi little g big I mu naught I. Okay, so this means that the probability of that this person is G and receiving G, and this guy is I and also receiving G. So in both cases, this guy is receiving little g. Okay, so in this case, then the prosecutor can actually get some payoffs, right? Otherwise, if it's the signal is acquit, then actually the prosecutor gets nothing, right? So this becomes 1 times 0.3 plus 3/7 times 0.7. This is 0.6. Okay, and this is greater than 0, of course, and it's also greater than 0.7, right? Okay. So here they convict, so the judge convict 60%, right, from this result. So here actually we are multiplying this by 1, but we don't need to do that, right? So they have the same result. Okay. So the judge previously, the judge actually knows that 70% of the people is good people, okay? They're innocent. But actually the judge is only convicting 60%, right? So that's the interesting part of this persuasion. So, and also the judge also knows that this signal is designed to maximize the probability of the conviction, okay? But although they know this, the judge knows this, the judge is still convicting less than before, okay? With than the case that without any signals, so any useful signals. So so in this case, then this prosecutor is successfully persuading this judge, right, by controlling their information environment. Okay. So let's finish this argument. Okay. So the judge knows this, is designed to maximize the probability of conviction, right? So those are just public knowledge. They all know this, right? But they still do this. So this is the interesting part of the persuasion, because they are better off, of course. So so then this the senator, the prosecutor, persuades the judge by controlling their information environment. Okay, so those are some intuitions. Okay, now let's draw a little picture to visualize this example. Okay, so I have some picture. So here on the horizontal axis, we have mu with the omega equals to guilty. Okay. Be careful of what we're talking about here, right? So now we're talking about the probability of guilty, the poster belief found guilty. Okay, so originally we'll draw the V hat here. Of course, we will draw the big V on top of that. So suppose that this is 0.5, this is 0.3, which is the mu naught, right? So let's say this point corresponds to 1. Okay. So it means that originally this V hat is a step function, right? So from 0, so it equals to 0. V hat is 0 if x is less than a half, and V is 1 if x is larger than a half. Okay, so it's a step function, right? So, all right. Okay, so we have, so the smallest concave function, which has the everywhere is no smaller than this V hat mu, is our big V, right? So that's the concavification. So here specifically it's something like this. So we first connect those two. Okay. All right. And from here it's just this, right? That's our V of mu, big V. Okay. And originally the thick black line is the little V hat mu. Okay. The step function. All right. So originally, this V hat of mu naught, which is 0.3, this was 0, right? But since we have this signal, okay, and we redistribute this 0.3 mu naught to two sides, to here and here, okay? So now our poster belief are on those 2 points, okay? So correspondingly, the V hat corresponds to those 2 points, this and that, those 2 points, okay? All right. So on average, it must be this point on top of that, right? On top of the mu naught corresponds to the V value of the V hat mu. Okay. All right. And we have those probabilities to redistribute this prior to this different post-series, right? You have the tau for that, specific probabilities for those two different numbers. Okay, so this V hat is a step function, of course. All right, and we already see that in the picture. So the optimal signal induces two posterior belief. Okay, optimal signal induces two posterior belief if judge observes little I, then this mu is 0, right? So correspondingly, this v hat of 0, it should be 0, just 0, right? Just from here. Okay, so if the judge observes little g, then this mu is 0.5, okay? Then v hat of 0.5 as the mu, this should be 1, okay? So just by concavification, that is tau, gives us that the probability of 0.4 for mu equals to 0 and 0.6 for mu equals to 0.5, okay? 0.6, 0.4, okay? And we can also verify that. Okay, all right, so here, and we first calculate this expected utility for the sender, so it should be expectation over tau for the v hat given mu is 0.6, which is just the convex combination for that, right? Using the same probabilities and get those results. So we can also verify the base plausibility. Okay, so it's simply mu naught, it was 0.3, and now it's 0.4 times 0 plus 0.6 times 0.5, and it's of course 0.3. And this center of course benefits from this optimal persuasion, and this is because that v mu naught now is 0.6 is greater than v mu naught than v hat mu naught, right? So this is the value of the optimal signal, right? So, and how do we actually calculate this pi? So pi is actually, so it should be constructed from the proof that we did in the previous episode, right? Using some sort of the pretty interesting construction that we did previously, and also this is what we used in the proof of for the splitting lemma. But actually now here we can just take a look at the picture and we know the result of that, right? But rigorously we can use this, right, to construct the signal that we are going to use for the sender to persuade the receiver. Okay, the signal. This is the signal we showed in the beginning of this example, right? So actually this is something here, right? So those are the signal. This is the signal that we can calculate or we can construct from here, right? Okay, good. So this is everything about the for the example and for some intuitions and some corollaries for the Bayesian persuasion model in the Kamenica and Gentzkow 2011 paper, and this persuasion actually helps the both agents to get a higher expected utilities, and this is a quite interesting result. Okay, by giving some commitment power for the sender to commit to a signal structure, and which signal structure can actually induce a distribution over the processor beliefs for the receivers, right? So that's the key part, the key idea of this persuasion game. Okay, good.